Here we are at lesson 33, multiple comparison procedure for means. Just know that we're going to go through Tukey's method, but that is just one of many potential options that you have. And the whole idea is lessons 31 and 32, we asked, hey, is at least one of these means different? We say yes. This is the follow-up. Okay, well, which ones are different? So in lessons 31 through 32, we used this example where we were looking at carbon materials. We had 4 different temperature treatments, 300, 400, 500, and 600 degrees Celsius. We looked at 5 specimens at each temperature level and measured the pore size. So we went ahead, we rejected the null hypothesis at the 0.05 significance level. We had an F statistic with 3 numerator degrees of freedom, 16 denominator degrees of freedom of 12.097, p-value 0.0002. And we conclude, hey, we have convincing evidence that the average pore size for one of the temperature levels is different than the others. It's not to say that all of them are different from each other, but at least one. So now the follow-up is, which means are different by how much? So we want to now investigate which ones are different. So can we just perform 2 sample t-tests? As is, it's a little sketchy, so no. Because the number of individual tests increases, the probability we reject one by chance also increases. So if we have 4 here, you don't want to just, you cannot, in fact, people will jump on you. You don't want to cherry pick and go, oh, I think these 2 are different, and just test to see if those 2 are different. Unless you knew ahead of time, ahead of looking at data, that you were interested in those particular 2, you need to actually do all the pairwise comparisons. So you need to compare 600 to 300, 600 to 400, 600 to 500, 500 to 4, 500 to 3, 400 to 3. You would have to do all of those pairs. So the idea is if we use a significance level of 0.05 at the individual tests, when we perform 20 tests, we would expect to reject 1 test just by chance. Multiple comparisons, we start talking about this thing called family-wise error. I've also heard experiment-wise. But the idea is we need to adjust our alpha values or our p-values to account for the fact that we are making multiple tests at once to keep the family-wise error rate at 5%. So if you run 20 tests, you want the probability, your type 1 error set at 0.05, you want that to mean the probability that I reject at least 1 test to not be any higher than 5%. So these are and when you make our simultaneous confidence intervals, the idea is you're simultaneously making a confidence interval for each pairwise comparison. It will be wider than the individuals. These are ad hoc, which means after the fact. So once you decided, yes, at least one of the pairs are different, and you decide to check all the pairs, it's considered something done after the fact. So we need to do this accounting for it here. So I'm going to talk about multiple comparison, and we need to adjust the significance level and or adjust the p-value. It depends on which method you use. I believe we're using Tukey's honestly significant difference. I think that's what it stands for. And it adjusts the p-value for us. Other ones, you adjust the alpha level. So here, if I suppose I want my probability of type 1 error to stay at 0.05. So it's that cutoff. If my p-value is below that point, I'm going to reject. So my probability of type 1 error is alpha. But suppose I do 3 tests and I do each individual test at 0.05. The probability I make at least 1 type 1 error, it's jumped up from 0.05 to 0.14. So like 14% of the time I'm going to make a type 1 error, which now might become unacceptably high. Let me explain what this means. So probability, at least one type type 1 error. So that's going to be 1 minus the probability 0 type 1 errors. Oops. In 3 tests. So throw back to back when we were doing probability here. So this is 1 minus, I'm going to put all in here, probability test 1, no type 1 error. Times probability test 2, no type 1 error. I think you're getting the gist probably. Then for the third, oops, I can spell. So what you end up doing, you end up saying, oh, well, 1 minus. So the probability you don't make type 1 error on these individual tests, if you set your probability of type 1 error to 0.05, it's going to be 0.95 times 0.95 times 0.95, 0.95 cubed, and that's where this value should come in. So the idea is I need to either adjust this individual significance level, or I need to do something that adjusts the p-values for me, because if I leave it as is, I'm going to have a really inflated type 1 error rate. It's not going to be acceptable. So that's what we're talking about, these simultaneous confidence intervals and whatnot. They make these adjustments for us. So we're going to do a procedure specifically that adjusts the p-value for us. So multiple comparisons with honest significant difference. Tukey, I don't even remember how long ago he was alive. It was a while ago. Multiple comparisons procedure. And so there are, I choose 2 possible comparisons. So in the example we're doing, 4 choose 2, because we have 4 groups. We want to know every possible way, like we can pick a pair out of those 4. You're going to get 4 factorial, 2 factorial, 4 minus 2 factorial. So you're going to get 4 times 3 times 2 factorial over 2 factorial times 2 factorial. 2 factorial is just 2. So you're going to get 6 pairwise comparisons. Absolutely, check that math. I'm just doing some quick mental math here. So this is when you want to make comparisons between means. And prior to, if you have decided you're particularly interested in specific pairs ahead of time, you don't necessarily have to do all pairwise ones. There are different procedures for when you choose to do that. And an example of that might be, maybe you have a control and you want to compare the control to 2 different treatments or something like that. You aren't interested in comparing the treatments to each other, maybe, or maybe you aren't, I don't know. You're specifically interested in comparing them to a control. That might be an example where you're not interested in every pairwise. So the conditions, they're going to be identical to when we were doing that single factor ANOVA conditions. And then the null and alternative hypotheses here. So here you can absolutely write out every single pair. You could say, hey, mu 300 equal to mu 400, mu 300 equal to mu 500, and so on. There will be 6 of them. I find it easy to just say k is equal to 300, 400, 500, 600, and I guess that's L. So L and K and L not equal to K. That's fine too. So this is basically saying, hey, by default, we're going to assume all of these pairs of statements are true. One specifically where you're saying they're equal to each other, and then the alternative is where they're not equal. So then we have family-wise confidence intervals. This is not something we'll calculate by hand. You'll have your point estimate, so the difference in sample means that you actually observed. times this Q star. And you might go, Q star, like here's a new type of critical value. Yes, Q is its own distribution. I feel like it's exclusively used for multiple comparisons. No, there is not a table that I've ever seen on this one. We will count on R or software to calculate this for us. Trust me, this is not something you want to actually be looking up in a real table. But we want to show you the parts that go into it. And then that's multiplied by square root of your mean square error divided by the numbers that are in each group. And note that this part will change a little bit if you don't have the same sample size in each group. So then we're going to get 6 different confidence intervals for the 6 different, like you'll have a confidence interval for mu 300 minus mu 400, mu 300 minus mu 500, and so on. There will be 6 of those. So when we run it, and absolutely, I strongly encourage you to look at the code that we've given y'all. So 2 key multiple comparisons, you do have to specify like what confidence level you want it at, because that's where it adjusts this p-value. It adjusts the p-value for you, so you don't have to do some weird math there. So here, this is saying, hey, the difference between, okay, I guess they did 400 minus 300. 500 minus 300, 600 minus 300, and so on. There should be 6 pairs. So for their diff, this is my point estimate. So this is like right here, this number here, this is x bar 600 minus x bar 500. This is the difference in sample means we observed in the actual samples. Then this right here, this is my 95% confidence interval. Specifically, it is a simultaneous confidence interval, which is slightly different. You saw on the last slide from the other ones that we've done. And then this is the p-value. So remember all of those in the alternative, it's a not equal sign. We are not stressing directions other than not equal here. So here, if you want to compare to 0.05, it looks like 400 and 300, that's a big p-value. We don't have strong evidence that 400 and 300 are different. We do have 500 and 300 look different, 600 and 300, 500, it's higher than 0.05, but notice there, and then 600 and 400. I really like having the visual here. I would have rotated these, but they kind of run off. So if the null is true, the difference is 0. So this dotted line. So if it crosses this dotted line, that's saying, hey, we don't have strong evidence that the difference between those two is not 0. So like 400 and 300, here's that lower to upper. That's what this mapped interval is. Yeah, no, it looks like that 0 is a value in that interval. And the giveaway is, if you look here, negative number, positive number, 0 is in there. Negative number, 0 is not in there. Negative, 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 positive, 0 is in here. Negative, 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 positive. So ones that go from negative to positive will have 0 in them. So that those 3. But it's these ones that don't cross 0 that we're interested in. It looks like we have strong evidence that 500 and 300, 600 and 300, and 600 and 400 are different. Meanwhile, we don't have evidence that the other pairs are different from each other. It does not mean, careful, we do not have evidence that they are the same. So if I want to look at another one, I have A, B, C, and D. Whatever those are, they're just generic labels here. And I wanted to go ahead and look at the differences. So here I want to say, well, which comparisons are significant at alpha equals 0.05? I'm going to look at the adjusted p-values. And if I get p-values, adjusted p-values that are less than 0.05, I'm going to reject. So looking here, it looks like B and A are different. The second one, that's less than 0.05. Yes. I'm not sure if this output is from R. It has a tendency to not give us zeros, but D and A look like they're different. So it looks like A is different from all of the others, for starters. It does not look like, that's a huge, C and B don't look different from each other, but we have D and B are different, and D and C. So let me see, look in here. B and A, C and A, D and A, D and B, D and C. Yes. I would have also said all of them are significant except C and B as well. And other giveaways, if you were looking at these are your intervals. Positive to positive doesn't have 0. Positive, positive, positive to positive. Oh, negative to positive. So this one will have 0 in it. Positive to positive, positive to positive. So if your signs in the confidence interval are the same, you're going to have a significant difference. It's either higher or it's lower. So that's handy. I am a big fan, quite honestly, of having this visual. So we did include code, so you can put that out there. Just know that if you're looking for ones that are different, you're looking for ones that don't cross that 0 line. So, lucky y'all, and you can or cannot, we have another example. Threw this together here. So we have some psychologists. They're in Lancaster University in the UK, and they are really, really interested in name retrieval methods. Oh my goodness, colleges with any class size smaller than 30 always go around the room and say 3 facts about yourself and blah, blah, blah. That kind of idea. So they have 139 students. They divided them up into 3 groups. They did this using a random mechanism. So they randomly assigned the students to groups. And each group had a different game that they played to help each other learn each other's names. So group 1 used the simple name game where they just have everyone go around the room and say their name. And so person 1 says their name, person 2 says their name, so on. Group 2 is the elaborate name game. So now when everybody goes around the room, they say their name and they also say their favorite activity. And then group 3, pairwise. So everybody is put into groups of 2 and they have to introduce their neighbor or their partner. So 1 year later, they go ahead and they reach out to the students and they find out what % of the names are recalled a year later. So percentage of names, here we're going to look at that as something quantitative here. Are the mean percentages of names recalled different for the 3 name retrieval methods? And goodness knows, they would love to know if one was much more effective than the others, they probably would use that more. So what is my response variable? So what is it that we're measuring from each student? It's going to be the % of names recalled after 1 year, which is going to be quantitative. Units, I know it sounds goofy, are just %. And that can happen, absolutely. You can have the scenario where your units are in %. So what is the explanatory variable? Is it quantitative or categorical? So we're trying to figure out what makes any of the observations different. It's going to be what game they played. So which type of name game was played? This is categorical. So they either played elaborate, pairwise, or simple. That's what we're going to call them. And then we want to ask about study design. So is it observational study or experiment? So things to know, the key differences between observational study and experiment is with an experiment, you assign the individuals to what group they're in and what treatment they get. Observational study, you just observe. You don't try to influence what groups people are in and what treatments they do. So in general, if there's a treatment, usually that should nudge you towards experiments. So not only was this an experiment, it was a completely randomized experiment because they took the 139 students and randomly assigned them. They didn't stratify the groups at all. They didn't say, oh, you know what, I need to block. They didn't do that. It's just completely randomized block design. They took all individuals and randomly assigned them to one of 3 groups. Doesn't sound like even number of groups if it's 139 though. So our null hypothesis here is the different name retrieval methods had no effect on the mean percentage of names recalled after 1 year. If this is the case, what is the mean of all groups in relation to each other? So it wants the null hypothesis in notation and in words. So here we're going to go with, right, it won't, yeah. So mu, I'm going to use E, P, and S for elaborate, pairwise, and simple. So yeah, I'm not going to need that much room. So it's equal to mu P is equal to mu S. My alternative, I'm going to write down here, at least one mean differs. So at least one of them is different from the others. So the null is saying the mean percent of names recalled after 1 year is the same for all 3 name games. And then let me see, probably word it slightly different. So the mean percentage here. So my alternative, at least one differs. So it doesn't mean that they all have to be different from each other, just at least one is different. So the mean percentage of names recalled after 1 year differs for at least one of the 3 games. So in general, when we ask for hypotheses, we mean in notation, but if we ask for in words, this is what we mean. This in particular, practicing writing the alternative hypothesis in words is extremely useful, because when you write up your conclusion for the hypothesis test, you will say there is blank evidence that, and insert this. There is blank evidence the mean percentage of names recalled after 1 year differs for at least one of the 3 name games. Oh my gosh, my handwriting is horrible, I'm sorry. So absolutely practice writing this. It is incredibly important. If you are unable to write the alternative hypothesis in words, it's going to be very, very difficult to do your write-ups. So then our next part here, so explore the data. So this is just giving us like an initial view here. So my simple name game, I had 50 in that group. I had 42 in the elaborate name game and 47 people doing pairwise introductions. That seems a little weird since they're supposed to be in pairs. Maybe we had somebody drop out. Actually, that happens a lot, especially if you follow somebody 1 year later. We have the average percent of names remembered a year later. We have the standard deviations for each group. And here's a box plot showing the 3 groups. So it looks like pairwise, that box is a little bit lower. Definitely the center or the median is a bit lower, although we'll be comparing the means. It's just the box plot has the median right there viewable. Elaborate has a big spread. It really is spread out. Simple, it looks like it's shifted a little bit higher. It definitely has a higher outlier. So yeah, I would just definitely say, hey, it looks like pairwise has the lowest. It definitely looks like it's probably skewed right. Like if you were to fold it in half at the median, it's a lot shorter on this side than it is on that side. But once again, you can't tell the exact shape from a box plot. But yeah, absolutely simple. It looks like it's a little bit higher. So does it appear that they have roughly the same centers? I mean, it looks like simple and elaborate. There's a lot of overlap here. I would say simple and pairwise, probably different. Pairwise, its center looks further away than the other two. So this really depends. So I might argue no, pairwise looks lower. Lower than the other two. Elaborate and simple. Which is interesting. You'd think if you had to introduce somebody, but then again, you'd probably only really remember your partners. Does it appear that the three groups have roughly the same spread? Not exactly, but similar. And we'll go into something more exact. In fact, I pulled these out intentionally. We're going to talk about that. So to test the above null hypothesis, what should we use? Single factor ANOVA. So that's what we're going to do there. So here, we'll go ahead, data. We have data in each group must be normally distributed or big enough sample sizes. So I'm going a little out of order. Sample sizes. Oops. For central limit theorem. So we can kick in for x bar E, x bar P, x bar S. That is going to be true, I believe. We have our smallest sample is 42. We should have big enough, big enough samples for the central limit theorem to kick in. Constant variation, I'm going to leave that for the last one. So independent observations. This is going to be true as long as if student 1 is in group 1, they can't also be in group 2 or group 3. As long as each student or each participant is only in one group, yes. So as long as that's true. And then constant variation or standard deviation. Standard deviation. We're going to look on the next page for that one. So here we talk about that constant variance condition. It implies the spread within each group is roughly the same. It doesn't have to be exactly the same, but it needs to be close or close enough. So one way we can do this is look at side-by-side box plot and try and determine, hey, are those spread out kind of similarly, which is what we were doing. We were eyeballing it. You can also look at the summary statistics. So specifically, we're going to look at the standard deviation for elaborate, standard deviation for pairwise, standard deviation for simple. And we're going to compare them. As long as none of them are at least twice as big as any of the others, we should be okay. So that's our rule of thumb here. So here, I went ahead, I did two different things here. I have my box plot here. I also showed residuals here. And looking at the spread, is it wildly different from group to group? It looks okay. It's not wildly different. Yeah, this one looks a little bit shorter than the other two, but I mean, it's not wildly different. So just looking at this, I would probably say, hey, they're probably close enough. If they looked wildly different, the spread did, then that should definitely give you pause. So then here's that rule of thumb. So this is a lot easier to actually double check. So if you take your largest standard deviation, so it looks like 20.0354, over your smallest standard deviation, and that's less than 2, then we feel safe saying we have equal variance here. So my largest sample standard deviation was the simple name game, so S simple. My smallest one was pairwise, so S pair. That's 20.0354 over 15.7032. I can tell you right off the bat, that's not going to be at least 2. 20 over 15 is not going to be 2. It's going to be more like 1.5. Yeah, it's about 1.5, which is less than 2. So yes, it's okay to assume the standard deviation for simple is the same as standard deviation for pairwise is the same as standard deviation of elaborate. So we can assume the variability within each of the groups is close enough to use this one-factor ANOVA test. It should work. So here, this is what we were talking about, right? That we love, and I mean we love, to fill out these ANOVA tables. It is our bread and butter. We love to do this. Absolutely. So sum of squares. This is degrees of freedom, mean squares, and then F statistic. You could probably include p-value, but I'll get to it on another one. So between groups, this is for treatment, this is error, and this is total. So here I've provided sum of squares total, and we will not actually fill out that part, and we provided the mean square error, and we're going to try and figure out the rest of the table. Believe it or not, we've given you enough information about the problem and the table, and that's a hint. You might have to use things about the problem specifically to fill out this column to actually fill in the rest of the table. So here I'm gonna degrees of freedom total, so DF total, that's going to be my entire sample size minus 1, so that's 139 minus 1, that's 138. So then I have degrees of freedom for treatment. That's going to be my number of groups minus 1. So I had 3 different name games minus 1. That's going to be equal to 2. Hint, 2 plus degrees of freedom of error is 138. So I can tell you it'll be 136. But degrees of freedom error and total, that's 139 minus my number of groups is 3. It's 136. So as long as you can have 2 of these, you can always find the third. I find it easiest to find degrees of freedom total and then usually degrees of freedom group, and then that gives me my degrees of freedom error. They should always add, the first 2 should add to the third. Okay, so now I have enough information to go and find my sum of squares error. That'll be my next one. Because I know my sum of squares error divided by degrees of freedom error is my mean square error. So my sum of squares error is these 2 multiplied, so 397.394 times 136 is equal to, sorry, I can't do that math in my head. I promise I did it though. Let me see. 54,045,584. Ew. Sorry, close to the edge of the tablet's a little hard there. So my mean square, my sum of square error there is 54045.584. And then what's cool is I know my sum of squares total minus my sum of squares error gives me my sum of squares treatment. So, sorry, sum of squares treatment, that's going to be that 60,155.5 minus that 54,045,584. That's going to be 6,109,916. So 6,109.916. So almost there. Oops. Then my next step, I know my sum of squares treatment, divide my sum of squares degrees freedom treatment will be my mean squares treatment. So it will be that 6,109.916 divided by 2 degrees of freedom. This would be 3,000 some odd. 3,054.958. 3,054.958. That's my mean square treatment. Now I just have to take the ratio of that, and that's my F statistic. So my F statistic is that 3,054.958 divided by 397.394. It's going to be 7.687. So my F statistic is 7.687 on 2 and 136 degrees of freedom. So 2 numerator degrees of freedom and 136 denominator degrees of freedom. And there you are. That's our table. So absolutely, that is like our bread and butter. We love to give partially filled out tables with just enough information to fill out the rest. It is something we do enjoy doing. So that does definitely require to know that you add down, you divide across kind of idea. There we go. So how many degrees of freedom are associated? So my numerator degrees of freedom were 2. My denominator degrees of freedom were 136. So my p-value, I threw this into R. It gave me a p-value. So using R, my p-value. And remember, with an F statistic or F test, they're always going to be one-sided. They're always going to be upper-tailed as well. We're never ever going to mess with the lower tail for the F distribution. So my p-value is 69 over 100,000. It's pretty darn small. And it's a very small p-value. So we're going to reject our null here. So bear with me. You absolutely don't have to listen to me read out loud what I'm writing. So we're going to reject the null hypothesis. So reject the null hypothesis at the 0.05 significance level. Ew. And then I'm going to put all the info here. So F stat equal to 6.687 with numerator degrees of freedom equal to 2 and denominator degrees of freedom equal to 136. P-value equal to 0.00069. And then I would say this is very strong evidence, or this is convincing evidence. So this is convincing evidence. And this is that part that I said, hey, hold on to how to write the alternative in words, we're really just going to take that alternative words and stick it right here. So absolutely, listen to me say the rest, check it yourself, whatever you want here. So that the mean percent of names recalled after 1 year differed for at least one of the 3 name games. And I have simple, elaborate, pairwise. Okay, so our p-value is small, so we reject the null at the 0.05 significance level. We had an F statistic of 7.687 with numerator degrees of freedom of 2, denominator degrees of freedom of 136, and a p-value of 0.00069. This is convincing evidence that the mean percent of names recalled after 1 year differed for at least one of the 3 name games. And I listed the 3 name games. From here, the follow-up is going to naturally be, okay, the average percent change was different for at least one of the groups. Which groups? And recall that we thought, hey, pairwise looks a little lower. That might come back out here. So now we're going to move on to step 2. So now that we rejected the null and said, yes, at least one's different, now it's our job to say, okay, well, which one's different? So absolutely, when there are only 3, it's easier to determine how many pairwise comparisons are going to be made. What are they? So I have 3 groups and pairs. So 3 choose 2. It's gonna be 3. But so 3 factorial over 2 factorial over 1 factorial. 3 times 2 factorial over 2 factorial, boom, boom, it's 3. So I could have simple and pairwise, simple and elaborate, and I can have pairwise and elaborate. And the idea is comparing simple to pairwise is the same as comparing pairwise to simple. Because if I find that simple is different from pairwise, I'm going to find that pairwise is different than simple. So order here is not mattering too much. That's how many. I have 3 pairwise comparisons. And that's what they'll be. So for each of them, we're going to go ahead and perform a 2-sample t-test. What are the null and alternative hypotheses? So we're going to even look at mu I is equal to mu k, where I and k, they're equal to E for elaborate, S for simple, P for pairwise, and we're not looking at when I and k are equal to each other. Absolutely, feel free to, you can actually write mu S, mu P, mu S, mu E, mu E, mu P. That's not too bad. There's only 3. It's a lot more tedious when there's more than 3. So, but this is what we would be looking at. So how many degrees of freedom will the t statistic have for each of these? So the t statistic here is going to have the degrees of freedom of your error. And it's going to be equal to your n total minus the number of groups. So I had 139 students total in all 3 groups, minus the number of groups, which was 3 groups, so 136. So my degrees of freedom for the t statistics that I'm calculating, it is going to be just the same as my degrees of freedom error. And then 17, what is the name of the type of error that could be made when you reject the null hypothesis? So if you reject the null, the only type of error you could have made, it doesn't mean that you made it, is type 1. Similarly, if you fail to reject the null, the only error you could have made was type 2. That's the idea. So here, which group means are different. So see this dotted line here? That's where 0 is. So this interval crosses 0, so simple and elaborate. We didn't find evidence they're different because 0 is in there. But it looks like pairwise and elaborate doesn't cross 0, and pairwise and simple doesn't. Which we can go ahead, we can corroborate. This is these are our point estimates. This is the differences we saw in the samples. These are put together. This is our intervals. So negative to negative doesn't have 0 in it. Negative to positive does. Positive doesn't have 0 in it. So because I'm doing 95% confidence intervals, I need to use alpha equals 0.05. So pairwise and elaborate, that looks different. That's lower than 0.05. Pairwise and simple. So pairwise is different than simple and elaborate. So what this really comes out to is, remember at the very beginning when we went ahead and we remarked on the box plots and I said, hey, it looks like pairwise is lower than the other two? This is confirming what we saw, that yes, pairwise is lower than the other two. Simple and elaborate are close enough that we don't have strong evidence that they're different, but we do have strong enough evidence to suggest that pairwise is different than the other two. So here, bonus slides, your turn, and our examples, so definitely very handy. We also included in Canvas the R code and whatnot. Definitely please take a look at it. We're definitely speeding up, looking at a lot of tests now. Please feel free to ask questions, and we'll see you next week.